Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and my guest today is Dr. Ian Stewart, who's an emeritus professor and mathematician at the University of Warwick in England. Ian, thanks so much for being here.
It's my pleasure. Thank you very much.
And I will say this is kind of nice for me to get to meet you and talk with you because I've read several of your books in the past, especially when I was in graduate school. One that I especially remember and have fond thoughts about is Letters to a Young Mathematician, which I read when I was kind of a young mathematician. And then I shared that book with my brother when he was going into mathematics. So we had a nice connection with that work.
Wow, that's fantastic. It's nice to know people actually read them.
Well, I think quite a bit, right? Because you keep publishing more, so there must be an audience out there. And I know some people might recognize your name from the Does God Play Dice? And then more recently, the Do Dice Play God books as well. But I want to talk to you about your newest book, which is called What's the Use? How Mathematics Shapes Everyday Life. And that's from Basic Books. So that book is the most recent one. I enjoyed reading this one as well. But I want to go back a little bit before, and I want to ask you about your own personal story. And at what age did you decide to pursue mathematics as a field of study? And then this book, What's the Use, talks about the usefulness of mathematics, especially the sort of unreasonable effectiveness and use of mathematics. But I just wonder, when you were young, did the usefulness or practicality of mathematics, did that play a role in you deciding to study math?
No, it didn't really. I
actually thought maybe that was the case, that it was sort of like, in retrospect, you found out all this unreasonable effectiveness.
Yeah, I mean, I preferred the pure maths to the applied when I was in high school. And when I was in university doing my first degree, we had to do both pure and applied. And I much preferred the pure. Looking back, I'm glad I did the applied, but it takes a while for that to sink in. I guess I started to get very interested in math. I was always pretty good at it as a kid. And, I had a good memory. I could do the sums. With a few glitches here and there, I tended to get the answers right. So it didn't scare me. I was pretty happy with it. And then I got, when I was about 15, a small group of us got interested in just doing almost sort of amateur mathematical research. We would play around with mathematical problems that were not the ones from the school book, maybe ones we'd invented ourselves, and just, sort of follow our noses and see where they led. So by the time I was 16 or 17, I'd already decided that I was either going to do math or physics. I was always interested in the sciences. From the age of 5, I was interested in astronomy and dinosaurs and stuff like that. But by the age of 17, coming up 18, I'd narrowed it down to math and physics. And then circumstances conspired to make it much more sensible to go into math, because I got a very nice offer from Churchill College, Cambridge University, which is one of the top universities in the UK. It was a new college. I was a grammar school kid, so working class background, wasn't one of the posh kids who always went to Cambridge. In fact, my school had hardly sent anyone to Cambridge. But for various reasons, I was given an offer to study there. And I still had a year to go before I had to take the offer up. So I studied more advanced math and I studied my physics, but it kind of decided in favor of math because there was the place at the university I wanted to go to. In retrospect, that was absolutely the right decision. And, I enjoyed the whole thing.
I think, having read the book, What's the Use? I think it's kind of fitting that you started with a natural curiosity and a play with numbers and a play with mathematical problems, and then later realized all this effectiveness and practicality of mathematics, because that's really the theme of the book, is that it's not just when mathematics sets out to solve practical problems that it's useful. It's also that when mathematicians play and explore ideas and create structures and ideas, those also can turn out to be useful, which sounds like a little bit of a microcosm of your career too.
Yeah, that's right. I mean, when we were discussing this possibility with the British and the American publishers, the publishers very quickly said, there's lots and lots of stories about how some important problem in the real world comes up and then people invent math to solve it. But what would interest our readers, we think, the sort of book you should write, would be math that was invented for a totally different reason, maybe 100 years or more before it got, important applications. Nobody expected it to be applied to anything. And then suddenly it turned out that it was very, very useful on some problem that the people who invented it in the first place would never even have realized could exist. So we were looking for surprising applications of surprising mathematics, of unusual mathematics. Mm-hmm. So that was kind of the idea.
Yeah, and so I think that took shape in the form of this book. Are there other inspirations, or were there other kernels of ideas that sort of led to What's the Use?
Yeah, there were various things. I mean, I actually did some industrial consultancy work with a group of mathematicians on a project for the spring making industry in the UK.
Which ends up being a chapter in the book.
It ended up being a chapter in the book. And it was a fascinating exercise because we had government funding. We had about 10 or 12 small companies making wire, companies making springs. And it was 5 years in all. And we would have every 3 months a meeting of everybody. So I got to meet people from the industry, from the government. They got to meet mathematicians. We had an engineer, and we had some people who actually knew about the core of it was what's now called the Institute of Spring Technology in Sheffield in England, who had a lovely engineer who had got the idea of what the project should be about and what we should try to do. So I told the whole story of that in the book. Mm-hmm. And so that was sort of my personal. But the math we used had not been invented for the problem that we applied it to. So it fitted the theme of the book.
Right. And I mentioned that you have, many other books that you've published sort of communicating mathematical ideas to a more general audience of people that are interested in mathematics and not just a pure research audience. But I wonder how you see this book, What's the Use? How do you see it fitting in with your catalog of other books?
I think it's different in the sense that the audience for this book is going to be self-selected as people who actually have some interest in math. I'm not sure that any of the diehard, I don't like math people would be persuaded, come on, you should like it because actually it's much more useful than you think it is. That would be lovely, but I don't think it's like that. But nonetheless, it's a book that kind of tries to set out a point of view on how math relates to the outside world and to our daily lives. And although some of my books touch on that, most of them are not like that. Most of them are more, hey, here's a really interesting area of mathematics, or let's take a historical look at the development of the subject and the people, that kind of thing. Whereas a book which, in a sense, tries to sell mathematics to the readers is a little bit different for me. I've been thinking about the possibility for some time, and my editor at the UK publisher thought he seized on this idea at one point, said, yeah, we should do that one.
So What's the Use does have a variety of mathematical topics and contexts that show up. There's political redistricting, there's cybersecurity, there's having a comfortable mattress and the springs that are involved in not just mattresses, but it's springs. Actually, I was surprised how many different things the springs are. Really
God, they're everywhere. They are absolutely everywhere. Most of them, of course, are inside the box and you can't see them.
Yeah. I'm curious about, which of the chapters or was one of the chapters sort of the earliest ones to come together where you're sort of like, oh yeah, I have that chapter. I have that story about an unreasonable effectiveness of mathematics. And then I'm wondering if there was what was the last chapter to kind of come together or to make the cut into the book?
Okay. I think certainly one of the very early ones where it was clear in my mind that there was a story to tell and how to tell it is the application to medical scanners. Right. So we have this wonderful technology now which can take three-dimensional pictures of the inside of the human body or of other things indeed. And it's just magic. Yeah. I mean, you sit in this this sort of tunnel and this ring-shaped thing moves over you and makes lots of noise and so on. And then on the computer is a picture of what it's like inside you, but nobody's cut you open. And I have some interest in Egyptology, so does my wife, and they use that to scan mummies.
Right.
Instead of unwrapping the mummy, which would destroy things, you just do a scan. Now, that is technology which, 30, 40 years ago was essentially impossible. But the mathematical story probably goes back 150 years or more. Mm-hmm. And it starts with someone who's trying to understand, Joseph Fourier in France, trying to understand the mathematics of heat flow. If you stick a poker in the fire and the end of the poker gets hot, or later on the handle gets hot, and he wanted to mathematically understand how the heat flowed from the hot end to the cold end, or any problem of that kind. And he invented a mathematical gadget called a Fourier transform, which essentially converts the heat problem into a problem about lots and lots of wiggly curves and how they fit together with each other. Mm-hmm. So you turn your heat distribution into a collection of wiggly curves. Later on, there's another closely related mathematical transform, which will actually give you a cross-section of some object. This transform is the one that gets used in the scanners. So the story mathematically leads from Fourier's transform to the Radon transform, which is the one that is used to essentially to take a slice of your body and then look at it from lots of different angles. And it kind of takes an X-ray picture from each angle. But the problem with an X-ray picture is it's two-dimensional. You can see there's a black blob in the middle, but you don't know how far away it is. But if you take pictures from lots of angles, you can reconstruct exactly the internal positions of everything. And so this Radon transform is the first step towards the mathematics of scanners. And of course, the scanners themselves were invented by physicists and then engineers and medical people. And the connection with the math was made fairly early on, but not immediately. And now that whole area is this wonderful combination of math, engineering, medical science, and it really saves people's lives. It's become a routine medical tool.
Right. And your chapter has nice images too to show like a very simple kind of two-dimensional projection through one slice. But then if we have another slice, then you can start to get more precision to realize, oh, if we stitch these together, we can get a three-dimensional model of what we're seeing. And I thought you did a nice job of visually helping us follow along that process. But now, of course, the computers can do it very refined, you know.
Oh, yeah. It's all in the computer. So the patient or the doctor or hardly anybody except the people manufacturing the machine absolutely need to know this math. But without a culture of math to get the ideas in the first place, these things would not happen. Mm-hmm. Yeah, I like to use pictures because I think, genuinely a picture tells 1,000 words, as they say. The right picture can make the whole thing obvious when complicated formula just obscures it. And I like to try to not just tell the story of what's happening, but try to explain a little bit of the math and why it works. I don't like to push too hard in that direction because, the readers are supposed to be enjoying this stuff and it's not a test. But I think it's always nice when you get a little bit of insight into the reasoning behind these things. Not just, gosh, wow, it works like this, but hang on, let me explain. Here's the problem. Here's what the math does for you. Here's how you put it together. Yeah, there's a lot of detail I'm skipping over. Half the things I'm saying aren't entirely true unless you add extra qualifications to what I'm saying. That's right. They give you the main idea.
I also wonder what was one of the last chapters to make it in.
I think one of the last ones, partly because it meant I had to write another one first, was the application of things called quaternions to computer graphics and to movie special effects. So, the way the chapter tells the story, you go to the movies and you see this fantastic image of a dragon who is, flying down towards a medieval village and breathing smoke and fire, and the village catches fire and everything else. And you get pictures from the dragon's point of view and the dragon flaps its wings. And it all looks amazingly realistic. And the question that most of us, computer gamers on the whole, do not ask, how do they do that? They're having too much fun playing the game. Moviegoers may look at it and say, hey, that's a fantastic effect. But again, you don't often sort of sit there thinking, I wonder how they did that. But it seemed to me it was a nice idea to take the lid off that area. And there's a lot of math in there. And some of it's very, very new. And I mention a little bit of that. And some of it goes back to the mid-1800s and getting into Victorian times. And an Irish mathematician who had got it into his head that there should be a different kind of number. So now we have to step back a little bit further. We're all used to real numbers, 0.351 or whatever, along the number line, like the marks on a ruler. You have a line and the distance along the line gives you a number. Well, there's another version, what's called complex numbers, where you have a plane, not a line. You have two different lines at right angles to each other. And these complex numbers, which at first sight seem completely ridiculous, because in complex numbers, negative numbers have a square root. And we're all taught at school, if you square a positive number, you get a positive number. If you square a negative number, you get a positive number. And there isn't anything you can square that gives you a negative number like -1. But in complex numbers, there is. And it's a new kind of number called I. And there's this whole amazing mathematics of the complex numbers with fantastic applications to physics and all sorts of things. They're widely used in electronics. Your mobile phone will be using complex numbers all the time. But the quaternions are a similar gadget, but instead of a two-dimensional plane of numbers, it's a four-dimensional space of numbers. Now, this is getting a bit wild. Is it 4 dimensions? What does that mean? And these numbers are a bit peculiar because if you multiply them one way round, you get one answer. And if you swap them around and multiply again, you get a different answer. So it's as if 2 times 3 and 3 times 2 are not the same. And this held up a lot of progress for William Rowan Hamilton, the mathematician who invented them, because he wanted 3-dimensional numbers and he wanted A times B to equal B times A. And it turned out you can't do that. And even with 4-dimensional numbers, you can't do that. But if you throw away that algebraic rule, suddenly you can. And he had this amazing vision at some point. Suddenly he was walking along by a canal with his wife, and suddenly in his mind came the equations for how to multiply these numbers. And he took his knife out and carved them into the stone of a bridge nearby. Now, it turns out, and what he realized and what he was trying to do, these numbers are brilliant for doing geometrical transformations. They are fantastic for rotating objects in 3-dimensional space or sliding them along in some direction. And in a sense, you've got rotations in 3 dimensions and a slide in another dimension. That's why it's 4. Well, of course, in computer graphics, you want to rotate things. If I've got my dragon coming in and it swerves in some direction, then the dragon rotates its position. It may also flex its neck and flap its wings, but the rotation is key. And these quaternions have the wonderful property that when you do calculations on a computer, the answers are never absolutely exactly correct. They're rounded off to some number of decimal places. Well, if you do the calculations for rotations in the most obvious way mathematically, when you get these errors of rounding off small, in the 5th or 6th decimal place in the numbers, and you keep doing this millions and millions of times to get your moving object, it stops looking the same shape. It doesn't just rotate, it distorts. Now, with these quaternions, the beautiful thing they have is you may get the slightly wrong quaternion for the answer, but it's still a rotation. And it's a rotation very near to the one you want. So the human eye won't notice. So if you use quaternions to do the sums inside the computer that's doing all the fancy work behind the computer graphics, your spaceship looks like a spaceship. Your dragon still looks like a dragon. And that's very important. It's also a pretty efficient way to do all the math.
Right. Yeah. It's just to run, to render the computer graphics is a lot more efficient with the quaternions. But like you said, it also will look better, especially when you think about it's not just the objects in the computer generated movie that are moving. The camera is also moving. And you talk about this in the chapter. You see, they want to have the camera come in and they want to have the camera swoop around. So that means every single object, even that rock that is just sitting there on the ground, has to rotate because the camera is, moving. So then once you realize how many calculations happen, the efficiency of the quaternions and the smoothness or the accuracy of how it looks matters a great deal.
A few seconds of movie is billions and billions of calculations. If you want really realistic stuff, it is absolutely humongous number of calculations.
Yeah. So that was interesting to hear about. And again, that distance of time, right? The quaternions developed in a different century for a different purpose. And then now we see it, in the box office and the theaters. And you also talked about too, there's also just the geometric ideas of using polygons to build the sort of the net web for the characters that you're designing. So there's that kind of simpler geometry of sort of building your characters in your world, but then of course, putting them into motion. That's where the quaternions come in.
Yeah, there's all sorts of geometry of different kinds that goes into these things. I think I list somewhere 20 or 30 different software packages that people use, and each one of them uses different kind of math. And there are special ones to get very special kinds of effects. In fact, there's some new ones which I didn't have time. By the time I found out about them, it's too late to put in. But for texturing the surface of objects, there's new math which actually goes back to the heat equation and to Fourier again. So if I get another edition of the book, I might update that bit.
Right. Thanks for sharing a little bit about some of those chapters. And again, listeners can look at the book and find several other examples of this, of mathematical ideas that get used in surprising ways, or for different purposes. I do want to ask you, though, like a lot of math educators listen to the podcast. And so I want to talk to you a little bit about students in school. They very often in the United States, and I imagine also in the UK, they will ask, when am I going to use this mathematics? When will I use this math that I'm learning? And what would you say to a student who is aware of your book and who maybe agrees with you that, like, yes, mathematics is very useful in society. And maybe the student even agrees, like, yep, some ideas that were very abstract end up having practical applications. And so they grant you those points. But what if they still say that student personally feels like, well, I don't have to know this. I don't have to deal with this mathematics. Other people are doing it and computers are doing most of it. So what would you say to that student?
I think the first thing I'd say is I'm actually quite sympathetic to their point of view. I understand where they're coming from. I mean, most of us have a subject that we didn't actually like very much. Our feelings about it would not have been changed if the teacher had convinced us it was really, really useful and important and everything else. So yeah, sure, but I don't like this stuff. And it so happens I like math and the student we're talking about doesn't. And I think if they've made a really serious, they're not just using this as an excuse. They say, I've listened to what you said, I've thought about it, and so on and so forth. I think what I have to say to them at that point is, well, the thing is that you are following a particular course of study for your education, and the powers that be have decreed, if math is optional, then okay, don't take it. But if it's compulsory, people, for various reasons which are not to do with you as such, the reason we teach math to everybody, certainly in the UK, it's completely compulsory in the schools up to a certain level, and a lot of students struggle with it. But the reason we teach them, well, there are several reasons. One is a rather selfish one from the point of view of British society. We need lots of mathematicians. Something like 12% of the workforce is in the mathematical sciences. They produce 18% of GDP. So they're punching above their weight, and they are needed. Now, how do you get a supply of very good mathematicians? You shove everyone through the obstacle course and you see who comes out at the far end. And from the government's point of view, this is one of the reasons for doing it. Another one is, well, look, basic math, a bit of arithmetic, basic geometry, things like that. You need them all the time. You may not even realize you're using them, but if you don't know what they are, you can't actually, let the computer do it. Sure, but you don't know how, it doesn't make sense when the computer gives you the answer. You have no idea whether it's right or wrong. You don't really understand what it's doing. So if you didn't do any math at all, you would be struggling to understand the equipment you're using. You can't punch numbers into a mobile phone unless you at least know what the number symbols look like. So at the one end, you need basic math for your own personal benefit. At the other end, society needs much more advanced math. It's also true educationally that if you study a subject at a slightly higher level, it makes you understand the lower level much better. So if you go through math to the point at which you get stuck, your understanding of everything prior to where you got stuck will actually be better. It'll be better than if the teacher has said, oh, don't bother with that. So it's a slightly nasty message. It's saying, look, I'm sorry, but A, it's for your own good. B, tough, you got to do it. C, you will be able to survive and possibly you will become a multi-billionaire without it. It is not essential. And don't, if it's really not to your taste, I'm happy that you agree that it's useful and important. And a lot of people don't even understand that. So that's great. And I wish the educational system did not push you into this position. But you'll have to talk to them about it, not me.
Of disliking it. Yeah. No, I think I appreciate the honesty, especially that you started with, and that you're sort of weaving throughout, that you're trying to actually be very genuine and honest with the student about it. I wrote an article called Cornered by the Real World, a Defense of Mathematics. And I also kind of caution educators or teachers from basically trying to mislead the student into how useful some of the higher mathematics is. I mean, in like daily application, you're not going to actually use the quadratic formula on a daily basis. You're not, So I think that honesty goes a long way with the students. Like, hey, let's actually be honest about this together.
Yeah,
some of this stuff is not going to be used on a regular basis, but let's still have a conversation about it.
Yeah, I tell you a quick story about my wife, who is a nurse. Math was one of her least favorite subjects at school. She grew up in New Zealand, and she really did not like math and didn't understand very much of why she needed it. And then when she was doing her nurse's training, of course, they had to know you had to know basic arithmetic to work out doses of medicine you were giving. She was working with children. You have to it's very careful to give the right dose, because it can be dangerous if you give even slightly wrong and so on. But she still felt that beyond basic arithmetic, there was very little she needed to do. And then later on, she had some children, went back into nursing and was training in ophthalmic nursing, eyes. And suddenly she needed to know about the mathematical formulas for the optics of lenses. She needed to know probability for the inheritance patterns of eye diseases, eye colours. In fact, she wrote an article for one of the nursing journals about the kind of math you will need to know as an eye nurse. And this was all stuff that, because she'd had some sort of mathematical education, she could pick it up again and make sense of it when she needed it. So that's perhaps one other reason. If you've got bits of math tucked away in your head, even if you didn't fully understand them, you may find later that they are very, very useful to you.
I have a couple of final questions that I ask most of my guests, and I want to get those in with you as well while I have you here. One is actually about your PhD, your doctoral study. So I always kind of like tracing the lineage and just geographically where people sort of did their doctoral trajectory. So I just wanted to ask you where you did your doctoral studies and who did you work with there?
Okay, I did it at the University of Warwick, which is where I've been for my entire professional career, except for 2 years in the States, 1 year in Germany, 6 months in New Zealand. So I did my PhD at Warwick. I came from Cambridge. I went to Warwick and I did a very abstract branch of algebra. It's related to the mathematics of symmetry, but you wouldn't have guessed that by looking at my thesis. It was lots and lots of equations and symbols and formulas. I did it under a lovely man called Brian Hartley, who was had been a student of an algebraist at Cambridge called Philip Hall. These are fairly well-known people. And for a long time, I did that. I went to Warwick in 1967 as a PhD student, did 2 years, got the PhD in 69, got a job there for 1 year in 69, and they made it permanent in 1970. So we're going back a long way. And round about 1978, 79, I changed my subject area almost completely. And I moved into dynamical systems, it's called, how, the mathematics of how things change over time. So it could be the solar system, the planets moving, it could be the weather. I was interested in the pure math of that, and I was very interested in pattern formation aspects of that. And through that change of direction, I met an American mathematician called Marty Golubitsky, who's now at Columbus, Ohio, at OSU. And I went to Houston, Texas, where he was at the time, and we spent a year working together, and we have been collaborating ever since. I retired 12 years ago, but I'm still doing research, and I'm still doing it with him. And it's lovely when you retire, you can do what you like, and you find out, well, actually, I quite like doing research still. I don't have to do it because of the job. It's just interesting. It keeps me amused. My wife says it keeps me off the streets. So the career trajectory was basically went that way.
Mm-hmm. Well, now I want to ask you if you'd had a completely different career. What if you did not have mathematics as a career? Can you imagine having done something else instead?
Well, I think one possibility, I was actually lead guitarist in a rock band in university when I was undergraduate. So I could have gone into the music business, though I'm not sure I have the right personality for it. But
well, speaking of punching above your weight, I think British rockers have always punched above their weight in terms of that island producing a lot of rock and roll.
That's right. I could have been a pig farmer. My grandfather had a pig when I was a kid, and the pig is the kind of family animal. Some people it's frogs, some people it's bears, some people it's cats, and in our household it's pigs. We don't own any pigs, but I can imagine being a pig farmer. Yeah, so that's also possible. It's something completely different.
Mm-hmm. Yeah, both of my grandparents had pigs, actually, and they were in different states and different families, but I had pigs on both sides.
Oh, wow.
All right, well, it's great speaking with you. The book is What's the Use? How Mathematics Shapes Everyday Life. Ian, it was great talking to you.
Thank you, Sam. Great.